3, 2, 1. All right, welcome everyone to Digital Earth, Our Warming Planet. Here we have Bob Raynolds, geologist and research associate here at the Denver Museum of Nature and Science. We'll also be joined by Chun, who is our curator of astronomy and will be flying tonight. And I would like to hand off the program to Chun right now. Take it away.
All right, well, thank you very much, Mitch, and welcome everyone. And as Mitch explained, Digital Earth is our way of exploring planet Earth from the comfort of your own home using planetarium software. And we have a lot of content to go over, so I'm going to keep my introduction short. But before we begin, I just want to acknowledge that the Denver Museum of Nature and Science is on land that was held by the Cheyenne, the Arapaho, and other tribes. And I want to introduce Bob Raynolds, who is a research associate and a geologist here at the Denver Museum of Nature and Science. And as I said, we have a lot to cover, so I'm going to hand it over to Bob.
Great, well, thank you very much, Chun, and thank you, Mitch, and welcome everybody to Digital Earth. And I'm actually I'm in an amazing place. It looks like I can hear the crashing waves of the Pacific Northwest on the Oregon coast, but actually I'm in the Denver Museum. It's a miracle, and the first time I've been here in a long time, but the technology allows us, and I'm here to integrate together with Mitch and with Chun. And our program this evening is going to be wide-ranging. We're going to cover, first of all, the basics of what's going on outside on the landscapes of the planet. You know, what's happening with climate, why is it happening, and some of the science behind it. And that'll set the stage for a discussion about some of the impacts, first of all, globally, in terms of resources and water and things like that. And then we're going to shift gears a little bit, and we're going to look at three different elements of the story where we here in Colorado are being impacted by climate change, and we'll be looking at ways in which things can be made better. So we'll be looking at mitigation strategies and approaches that have been taken here in Colorado to make the world a more livable place, a nicer place to be. And then we'll end up with some quotes from some young people, and then I'll try to leave some time for questions and answers towards the end. We're intending this to be about an hour long, and it might be that at the very end we have a few questions that could be put into the chat, and Mitch will help us organize the questions so that we can have a little bit of a dialogue when we're near the end. I'm going to start out by just reminding everybody that in this century, in the last 20 odd years, we've seen an unprecedented collaboration globally of people looking at climate and climate change. And the program through the Intergovernmental Panel on Climate Change, which is abbreviated IPCC, you'll hear that acronym from time to time, that really represents one of the largest collaborations of scientists that has ever happened in our civilization. And of course, many people got together to figure out the vaccines for COVID. Lots of people have gotten together to figure out, technologies associated with the human genome or running a nuclear reactor. But in terms of getting large numbers of scientists, many thousands of scientists together and having their information synthesized systematically and carefully has never happened before. And so this study of climate change has brought our civilization on Earth together in a way that's never happened. And it allows us to benefit from the wisdom of so many different people from all over the world. And the picture that we see is challenging. And for those of you who are joining us maybe for one of the first times, this program, Digital Earth, is running now in parallel with a program called Digital Earth Academy. And Digital Earth Academy is loosely taken from Khan Academy, but it's a program that's designed to reach out to young people. And the Denver Museum of Nature and Science is an awesome institution supporting the educational community, not only in Denver and in Colorado, but nationwide. And so we do Digital Earth Academy to reach out to young people. These would be grade school students typically across all of North America. You have kids from Alaska, kids from all over the United States joining us. And I bring that up just to mention that we're going to show you a couple of the tricks that we've used to reach out to younger people in our program this evening. And we think that people, kids of all ages will enjoy some of these tricks. And Mitch and his colleague Asa have helped put some of these together. So hats off to them. But having mentioned the IPCC, which is the Intergovernmental Panel on Climate Change, it recently came out with a report. Many of you would have read about that in the papers. And the conditions are getting increasingly challenging in many parts of the world in a variety of ways. And this idea of continuing to collaborate and cooperate is underlined by the United Nations climate change conferences, which happen periodically. And there's one coming up this fall in Glasgow, in Scotland. And that's called, it's Climate Change Conference number 26, and it's abbreviated COP26. You'll hear about that, and that's going to be in October and November in Glasgow. And again, I need to stress that these global gatherings of scientists and the global integration of scientific data that's our tool to success. I mean, we have huge challenges ahead, but we've got massive numbers of people working on these challenges. And I'm fully confident that we'll see a variety of mitigating solutions coming up. And I'll mention some of them this evening. So I'll introduce you to some of them. But let's plunge into the data. And I warned the students that I was going to show them some graphs. And so there are going to be a couple of graphs here. But let's look at the first graph, Chun, and we'll look at Charles D. Keeling's graph. And the Keeling curve, which is about to appear in front of you, is one of the most important graphs that you will deal with in your lives. And it was created by a fellow named Charles Keeling starting in 1958. And he's measuring the atmospheric composition of carbon dioxide, or the concentration of carbon dioxide in parts per million in the atmosphere. And it's a wonderful story. Some of you might have heard it. We may have told it to you in earlier programs, but this fellow Keeling was a very tenacious guy, and he had the hypothesis that he could measure the changes in carbon dioxide in the atmosphere. And initially they started measuring them in various places, and the data was fairly noisy in the beginning. And he settled on measuring them up at the top of Mauna Loa volcano in Hawaii, a place that's out in the middle of the Pacific Ocean, not near any industrialization, and a place where he thought he could get a clean sample. And in fact, he was able to do that. And these data have been replicated in many different places around the world. And I would invite you, if you're interested in this, you can look on the internet and you'll see we actually have data collected from Niwot Ridge, which is behind Boulder. So there is a curve like this with data showing the carbon dioxide composition of our atmosphere right here in Colorado. It doesn't go back as far as this data set here. This is the most extensive data set. And if you look at the curve very closely, there's one or two places where there's a slight gap, where there was a lack of funding. And Charles Keeling, you'll hear him called David, his middle name's David. I think he went by David, but it's complicated because his son Ralph is also an atmospheric scientist. And so there's a Ralph Keeling that'll be in meetings. Unfortunately, Dave Keeling is no longer with us, but his curve lives on. And we gather this data very carefully now. And it indicates a systematic rise from somewhere on the order of 300 parts per million on the left-hand side back in the 1950s, up to in the vicinity of 420 parts per million right now. And again, you might think that's not very big numbers, but it has big effect, as we'll talk about in a minute. Let's look at the next graph, which is just a blow up of some of the most recent years. And here I just want to emphasize that the concentration, again, in Mauna Loa has a cyclicity to it. And you can see it's sort of like a sine curve going up and down. And I might ask you to ponder a little bit why that might be, why the carbon dioxide content at Mauna Loa would go up and down on an annual basis. And I'll give you a clue by saying that when we go to the South Pole and measure the same information, we also get a sine curve, but it's out of phase, means that the highs in the Mauna Loa area are lows in Antarctica and vice versa. And if you noodle on it a little bit, I'm looking for excited chatter in the chat here with people chiming in as to why that might be. And the chat is unusually quiet, or maybe I can't see it. But in any case, the reason is because the Earth is a sphere, and the northern hemisphere in the summertime, the plants are building their leaves, and they're putting on weight, as it were, and they're absorbing. Yes, I'm seeing it. Good for you. Herb's got the right answer. So what's happening is during the annual cycle in the northern hemisphere in the summertime, carbon dioxide is taken out of the atmosphere by the growth of plant material. And in the wintertime, it is returned to the atmosphere through the process of decay. And of course, that's opposite in the southern hemisphere. And the globe mixes relatively easily in a latitudinal direction. It doesn't mix easily in a longitudinal direction. So eventually it'll all mix, but on an annual basis, we see this disparity between the northern hemisphere and the southern hemisphere. But suffice it to say, the trend is going up and has continued to go up despite even the COVID. You know, if you look closely at these curves, we all hope that maybe we'd see a little dip during COVID times, and that hasn't been particularly clear. Now, what is the implication of this? Well, the carbon dioxide is a greenhouse gas, and the greenhouse gas is responsible for the change in the temperature of the planet. And basically, you can think of the greenhouse gases, which is things like carbon dioxide and methane, and actually water vapor. Water vapor is the biggest player. But as you increase the composition of greenhouse gases in the atmosphere, it acts like a blanket, and the Earth receives energy from the sun, and it reflects and radiates that energy back out into space. But as it's reflecting it back out, that energy is intercepted by the blanket of greenhouse gases, with the net effect being that it warms the planet. And you're seeing a model here of global temperature changing through time. And the reds, of course, are warmer, and you can see a strong warming of the Arctic or high latitude areas. And this is largely because of we call it the albedo flip. The diagram is just redoing itself here, so it'll come back again. And the time period here is roughly 1945 to 2012. So that last warm image was a few years ago, actually. But the northernmost latitudes are warming relatively rapidly because we're replacing sea ice, which is very reflective, reflects a lot of energy. We're replacing it as the ice melts with open water that absorbs energy very efficiently. So we call that the change in albedo, or the albedo flip. Albedo means the reflectivity of energy. And here is talking about that. So this is what's happening. The higher latitude areas are getting warmer. And this is something that was figured out by a woman named Eunice Foote back in the 1850s. And she did experiments where she put carbon dioxide and other gases in glass tubes, and she measured the temperature of the glass tube as a function of a time when it was exposed to sunlight. And Eunice demonstrated this in the 1850s, and her star is rising as people are finding her work. There's several other people that worked on it as well, people like Tyndall and Arrhenius, some of you might have heard of, and of course they received a lot of the credit, but Eunice did her work before they did, and credit is swinging in her direction. In addition to the change in temperature that you're seeing here, there's also what we call the other carbon problem. And this is a map showing the pH of the oceans. There's a little piece of litmus paper glued on the screen on the right. And the shifting from the blues into the lighter blues and the pinks is an increase in acidity of the ocean as a function of the carbon dioxide partial pressure that's over the water. And the carbon dioxide is mixing into the ocean. And again, this is a cycling thing. It shows 1980 and is projected to the year 2070. But you'll see in the northern, up off of the west coast of the United States, you'll see as it goes through time, it's starting to change the color. There you'll see the pink is coming in. And as the last part of this thing was a computer model, but the early part of it is based on data. And of course, the pH of the ocean is critical to a lot of the biology in the oceans. The critters that live out there behind my shoulder here, Many of them have calcium carbonate shells. And as the calcium carbonate is exposed to increasing acidity, it is less and less stable. So there's a concern that there'll be challenges to the food chain in the oceans associated with the changing pH. Let's continue our story. And one of the other things that's happening on a global basis is sea level change. And this is a wonderful graph. Again, a graph. The students were all warned ahead of time that they'd have to look at graphs. And here you can see it change through time. And it's mean sea level, that's MSL in millimeters over on the left-hand side. And then it's going from 1990-ish to about 2021. And the colors there are different satellites. And these are a series of satellites that are orbiting the Earth, and they're measuring the surface elevation of the ocean using radar altimetry. And they're getting very precise measurements. And as one satellite fades out, another satellite takes over. And so you can see a series of different colors on there. But the net effect is pretty clear. And this data is actually compiled at the University of Colorado Boulder. There's a fellow I visited with him, and he's gathering this data, and he puts the next dot on the curve as the satellites gather their data. And of course, there's thousands and hundreds of thousands and actually millions of measurements that go into this. So it's very robust information. You know, we used to measure sea level with a stick stuck in the sand. Now we measure it very precisely. And the rate of increase of sea level is about 3.3 millimeters per year. And it's getting a little bit faster. There's a thing there that says acceleration. You might notice that. But, you know, I might say that 3 millimeters per year is not that much. It's about the thickness of a penny maybe. But I'm a geologist, and 3 millimeters a year is going to get our full attention. We'll talk more about that in a little bit. We've also got a map of sea level rise, which is a very interesting feature. And the redder areas, sea level is rising a little bit faster than the yellowish areas. And this is when I first saw this map, I was actually shocked and surprised. It's from the Science on a Sphere database assembled by NOAA. And you can see quite a variety of patterns on here. And it's in part wind. You know, there's wind and there's gyres. So off of South Africa, those are gyres and eddies, and there's wind patterns. And so the actual rate at which sea level is rising varies, as you can see, in a complicated fashion. It's not just a flat surface. And then you've got to take into account the fact that some of the continental margins are either rising or subsiding. In many cases, they're subsiding. So the global sea level rise has to be taken into consideration together with the rate at which the land is moving as well. And it's not a pretty story in many places. While we're talking about water, I'd like to talk about the water on land. So the water in the sea is coming up. And incidentally, the sea level is coming up because of melting of ice that's on land, and also the thermal expansion of the water. So as the world is getting warmer, the oceans, of course, are getting warmer, and the water is expanding. So sea level is rising because of thermal expansion and melting of ice on land. And depending on a little bit on whose numbers you look at, it's about even, but different people have slightly different numbers on the proportional contribution of those two ingredients. But the net effect is, of course, the sea level is going up. On land, on the other hand, we've got a situation we say the wet areas are getting wetter and the dry areas are getting drier. And that is going to affect us here in Colorado. Chun's going to turn on the current drought map, looking at the western part of the United States in particular. And you can see here the red colors represent drought conditions, and the darkest red, the brown red, is extreme drought. And this is a map that's updated every Thursday. So this is an up-to-date map. And you'll see that the area of Colorado and west is particularly dry. So the west slope of Colorado going into Utah, Nevada, and Southern California, very dry conditions right now. And of course, this is impacting the Colorado River. And the Colorado River, as you know, has its headwaters in Rocky Mountain National Park for the main Colorado, and then the Green River comes in from southern Wyoming. And all of those areas are in drought conditions of one level or another. And the net effect is our reservoirs are at critical low levels. And Lake Mead, some of you might have been hearing the news about it, but it's at 35% capacity right now. And there's huge bathtub rings all around Lake Mead. And the city of Las Vegas, pictured right here, is getting its water from Lake Mead. and Lake Mead is shrinking. And it's got the full attention of the people in Las Vegas. You can see the bathtub ring there behind the Hoover Dam. And not only is Lake Mead at low levels, so is Lake Powell. Lake Powell is even lower. Lake Powell is at 31% of its volume right now. So Lake Mead at 35%, Lake Powell at 31%. Why does it matter? Well, it matters because 40 million people live in the downstream areas of this river system. And I've made the analog to some of my colleagues about the Nile in Egypt or the Indus River in Pakistan. The Colorado River rises from the high mountains from the snowmelt and precipitation, and then it flows through a desert, and there's relatively little tributary water into the Colorado system once it leaves the state of Colorado. And in order to supplement the water in Lake Powell and ultimately Lake Mead, we're actually draining reservoirs on an emergency basis right now. And we're draining the Navajo Reservoir, which you'll see at the south border of Colorado. It's where the San Juan River flows into New Mexico and then goes over to the Four Corners. That reservoir is taking a drainage of 20,000 acre feet. Right now, they're lowering the level of the water in Navajo Reservoir. They're also lowering the level of the water in the Flaming Gorge Reservoir, which is up on the border of Wyoming and Utah, just at the east end of the Uinta Mountains. Flaming Gorge Reservoir, they're going to drain that by 125,000 acre feet to contribute more water down into Lake Powell. And then in an area that some of you might have been able to visit or have had friends that have visited it, the Blue Mesa Reservoir, which is right near Gunnison, just west of Gunnison, between Gunnison and the Black Canyon of the Gunnison River, is Blue Mesa Reservoir. And this reservoir has been lowered dramatically in the last several weeks. They've taken 36,000 acre feet out of it. And these numbers don't mean very much to me, but the right-hand side of that reservoir is not there anymore. There's a river running down it. And the lower part of that reservoir is falling rapidly. The marinas have all had to close. And anybody who's got friends or colleagues who live down in Gunnison or in this area will be hearing about it because you drive right by that reservoir if you drive between Montrose and Gunnison. And it's a pretty shocking sight. It's at 32% capacity right now and falling fast. And all of this taking of water from these reservoirs in Colorado and in Wyoming is going to contribute only 3 feet of elevation down at Lake Powell. And again, why does it matter? Well, they're concerned about electricity generation at the dam. So the Glen Canyon Dam is a hydroelectric dam, of course, on the end of Lake Powell. And if the reservoir level falls too much lower than it is right now, they'll no longer be able to generate electricity at the Glen Canyon Dam. And then, of course, there's concern about the Hoover Dam, which is the dam for Lake Mead. So these water issues are playing out not only in terms of the water resources available to the 40 million people who rely on the river for their sustenance, but it's also affecting our capacity to generate what we might call renewable energy in the western part of North America. And if we can't generate electricity using renewable energy in the near term, we're probably going to have to use fossil fuels. So that's a irony, because it'll of course exacerbate the carbon dioxide problem, which is what's leading to this challenge as an overall issue. I think the other thing that we can show is here's the precipitation pattern. And it's really important for people in Colorado to appreciate that the lion's share of the moisture that comes to Colorado comes as snow up in the mountains. And that snowfall has been erratic over the last few years, and particularly on the west slope, west of the Continental Divide in the last couple of years, it's been very low. So the incoming water into the Colorado River system from the traditional headwaters here in the mountains of Colorado has been reduced. There's all kinds of other questions about this. Some of you might have heard about the fact that as the west is getting drier, there's more blowing sand and dust, and we get the dust on the snow, and that accelerates the melting of the snow. We like it to not melt quickly because we essentially use the snowpack as a water storage so that we get our water evenly distributed over the course of the summer as the snow melts. If it all melts very quickly, that's not a happy picture for us. Chun has turned on the river systems here, and he's also showing the trans-mountain diversions in yellow. And as most of you know, there's a wide series of tunnel systems that bring water out of the western slope, literally underneath the Continental Divide, to feed the Front Range urban corridor. And we've got a tunnel system that comes out of Grand Lake. We've got a tunnel system that comes out of Dillon Reservoir. And we've got a couple of other tunnel systems across the mountain systems that are vital for our water supplies here in Denver. And as I take a sip of my coffee here at the Denver Museum, I've got this wonderful cup of coffee with a beautiful SCFD mug. Thank you, SCFD. Half of the moisture in this coffee cup is Colorado River water. So half of Denver water, half of their supply is trans-mountain diversion. So the question that I've got to ask as I look at this system of challenges facing the Colorado River drainage, I'm hearing them curtailing reservoir levels and irrigation on the west slope, but that's going to come home to us here in the metro area. The time will come, maybe this fall, where we will recognize that our entire river system is connected. We need to cooperate and collaborate with our downstream partners in the water system, and we may well have to reduce our use of water here in the Front Range. We haven't really heard this yet because, interestingly enough, the drought conditions are mostly west of the Continental Divide, but the impact of that drought is going to be felt by us. You'll see there Chun showing the Central Arizona project and some of the canal systems that take the water from the Colorado River over into the Imperial Valley of Southern California. And those areas are being severely impacted. Arizona is having to reduce their irrigation by 18% next year. So the farmers in Arizona are taking an almost 20% cut in their water supplies for their agriculture in the Phoenix area. And that's going to be this next growing season. So we've had a discussion of where things are and what's going on the planet and what's going on in Western North America and in Colorado. And I want to now bring it a little bit more to our present conditions from the standpoint of what we're feeling as citizens. And I'm going to start with the heat, feeling the heat. And this is a diagram that shows the late June conditions in the Pacific Northwest. And you all read about the terrible, there was a heat wave there. This is June 28. And again, the red colors are representing unusual warm. And the western part of Oregon and western Washington state and up into British Columbia had shockingly hot conditions. They talked about a heat dome. There was an unusual weather condition that just focused a super pile of hot air right in that area. And those poor people suffered 110-degree plus temperatures, as many of you heard about. And the heat is not homogeneously distributed. So as you look at that map, the color code represents temperature, and you'll see that some areas are relatively cool, other areas are quite hot or warm. And this is a phenomenon that happens at multiple scales. And we want to give you the example of the urban heat island. And I bring it up because it's something that we can all experience and relate to. And we've got a map of Richmond, Virginia here. And there's a wonderful story in Richmond, Virginia. There's a fellow named Jeremy Hoffman who's with our sister science museum in Richmond. And here's Jeremy, and he outfits, he's got a vehicle with a thermometer and a GPS system. And he's got the volunteer there with his map, and he's going to hop in that car and drive around Richmond and record temperature and position. He's also got people on bicycles with the same technology. And so Jeremy has been able to make the map that we'll see here. We'll go back to the map and you'll see Richmond color coded by temperature. And it's a little bit of a computer exercise. He hasn't had any people go every single place, but what he does is he uses the data from the people who've been out gathering temperature according to time. He puts it into a computer model that takes into account surface materials, and he creates essentially a model of the entire community of Richmond. And you can see that some areas are hotter and some areas are cooler. And when we talk about an urban heat island effect, it's really an archipelago is maybe a better way to think about it. And here you can see that some areas in Richmond are definitely hotter than others. And this ties back to the architecture of the city. And the architecture of the city, of course, we're talking about the hardscape, the paved ground versus areas that have park and have trees. And where you have shady areas, as we'll demonstrate in a minute, you get cooler temperatures. And where you have open expanses of pavement, you get hotter areas. And sadly enough, as you might imagine, there's a social equity overlay on this, because the areas that tend to be less resourced, having less resources, tend to be the areas that have less trees and tend to be more industrialized. And so there are demonstrable correlations between sort of the quality of life and the temperature and the resources of the community, which translates into the wealth of the community. You'll also notice on the right-hand side of the map, there's an airport there that's super hot. It's because of all the expanses of runways, presumably. Let's bring this same model closer to home. And we've got a map here that's not quite as detailed, but for the city of Denver. And here you've got the Landsat composite of Denver. You can sort of see the color code, and you can see greener areas and less green areas. And now if we put a temperature map on this, which was put together in part by Trust for Public Lands, here you can see the same effect, that areas that are in red color are warmer, areas that are intermediate are in orange, and the areas that are a little bit cooler are in the yellow colors. And then the parklands are shown in green. And you'll see the city park right in the middle, right near the museum where we are, is a nice green area, relatively cooler, presumably. But then you'll also notice that the downtown metro area and some of the industrial parts of town up to the north, up towards Commerce City, are the warmer areas in Denver. And there are analyses and studies that have been done that show that, like in Richmond, in Denver, we've got a situation where there's a correlation between the heat island effect and the character of the communities. And those communities that have been able to plant trees and have more parks tend to be cooler, and those communities that have more open pavement and open ground tend to be warmer. And we can demonstrate that again and again. And I think we're going to send Chun out to see if this is really true in Denver. So let's see if we can send Chun out on a mission. He's going to stand in the middle of the street here in downtown, and he's got an umbrella, so he's providing shade to his thermometer, but he's standing on a sun-baked street in downtown Denver, and he's looking at the temperature. Chun, what temperature is it there? I'm trying to look at your thermometer, Chun, and see what temperature is it? Oh my goodness, look at that. It's 101 degrees where Chun is standing there on the pavement. Oh my gosh. Chun, let's get you to a shady place near the museum. There we go. And so he's coming in towards City Park, and he's going to do the same experiment using the same conditions. So he's got the same umbrella, the thermometer is the same distance from the ground. The setup is identical, same day. And now let's see what temperature it is where you are now, Chun. Tell me what temperature it is where you are there standing in the shade of a tree in City Park. So we're going to look at his thermometer. Chun, what do you got? Oh my, look at that, 92 degrees. So it's almost 10 degrees cooler in the shade than it is out on that city street. So that's a demonstration. And I want to emphasize that this is pretty low tech. I mean, Chun went out there with his thermometer and documented these differences. And we've chatted a little bit here at the Denver Museum about maybe having some kind of a citizen science program to go out and maybe replicate some of the things that they're doing in Richmond, Virginia, to better document the urban heat archipelago effect in the city of Denver. Another thing that's important here is to look at the color of the roofs of the buildings. And as you look down from space, you'll see that some buildings are brighter than others. And we did an experiment for our younger people, but I'm going to share it with you guys to look at the effect of the color of a roof. And Mitch and Asa built us a Lego city, and then they shine a bright light on it, and they're measuring the temperature using the thermometer that we had up at the front door, and they're measuring the temperature of the rooftops of their Lego city. And here you can see, if we hold the scene here, this is in degrees Fahrenheit, and we've just got a bright light shining on a Lego city, and you can see a tremendous range from 67, about 68 degrees, all the way up to 79 or almost 80 degrees Fahrenheit, simply associated with the color of the roof of these Lego buildings. And don't you think it'd be the same in our city of Denver or in any other city? So here's something that can be done. And we like to point out to people that there are strategies to make our urban conditions more favorable. And something as simple as changing the roofing material, maybe requiring people to have lighter colored roofs might be a strategy. Planting of trees. And I was talking to the young people about planting trees. And of course, some people don't live in a place where there's any room to plant trees. But I said, well, you can even have like a vegetable garden. And if you've got a terrace or something, you could have tomato plants. It doesn't need to be a full-blown tree. You can just start to put some vegetables out there and turn the ground green and provide some shade. So this is the kind of thing that we can do. And many of you know the city of Denver has had a tree planting campaign. It was instituted, I think, back when Hickenlooper was mayor. And I'm sure it's still going on. And there are lots of ways in which people can get involved and can plant trees in their own home or in their neighborhood or in their community. So we can make a difference in making our communities more livable by some relatively simple strategies. Now we're going to shift gears a little bit and talk about the forests of Colorado and the impact of climate change on the forests. And this is going to include thinking about fires and thinking about smoke and thinking about the trees and the bark beetles and the issues that are associated with the warming of the West and the drying of the West. And one of the things that we've all noticed here in the Front Range in the last couple of summers especially is the burning of the forests. And Chun's going to bring us into the Pacific Northwest here. And we've got it's a false color image to give us the pink colors, but you're looking at a fire from space. So we're up at satellite level looking at a fire burning in the Pacific Northwest. We're either in southern Oregon or northernmost California here. And you can just see the massive plumes of smoke stretching out towards the east from the flaming forest there in the center part of the image. Well, that smoke doesn't stay out in the west. If we were to stand back and look at a national map of smoke distribution, you'll see that that smoke, and here's a NOAA compilation from just a few days ago, and you can see that that smoke from California is swirling around, and it partly goes west, depending a little bit on local wind patterns, but ultimately it's picked up by what we might say the trade winds, and it's carried east. And you'll see that the smoke goes all the way to Labrador and to the eastern part of the United States. And of course, en route, it's going across Colorado. And so, as most of you know, we've had unusually poor air quality this summer, as well as last summer, in part because the smoke from the burning fires in the West, which include fires in Utah and in Colorado as well, of course, but that smoke comes to us in the Front Range area, and indeed to our neighbors out to the east. And Colorado, in the Front Range area, had some of the worst air quality in the world this past summer. And for people who are asthmatic or suffering from respiratory diseases, the quality of the air is, of course, a vital human health issue to be dealt with. So this is something that is a challenge for all of us. And we might say, well, why are the fires there? And there's been a lot of discussion about why the fires are burning, but a lot of it has to do with the conditions in the forest. And if we now go and look at some of the forests in western Colorado, we're going to be able to step down towards the area on the west, in the headwaters of the Colorado River, actually near Grand Lake. And some of you have been out there. You know, of course, that was an area that burned very badly last summer. And as we go to look at the conditions on the ground in that area, it's very striking that the forests have suffered severely. And these are lodgepole pine forests. And as Chun gets us in closer, we've got Grand Lake and the southern western edge of Rocky Mountain National Park here, headwaters of the Colorado River. You'll see interesting patterns. There's some road patterns, there's some clear-cut patterns. But if you look at the trees on these slopes as the computer comes into focus, you're going to see a gray color. And yes, there's some green trees there for sure. But these gray slopes that you're seeing right here, and which in fact characterize much of this area, are the trees that have been killed by the pine bark beetle. These are lodgepole pines, and they have been decimated by the pine bark beetle. And the pine bark beetle is in this area because it's always been there. It's a native beetle, but it's particularly active in this region because the winters have been relatively warm, and the beetle, which normally would be killed back in the winter times, has been able to live through the winters. The summers are longer, and the beetle is able to have 2 cycles of reproduction every summer. So the numbers of beetles are growing rapidly, and the trees have been weakened because of drought and warmer conditions. And so it's been a perfect storm for the loss of lodgepole pines. And it's not just lodgepole pines, and it's not just Western Colorado. The loss of trees has been regional, and we might see a map of that in a couple of minutes. But the net effect of this has been to create a landscape that is ready for combustion. And you know, the dead trees are dry and they burn very easily. The live trees also will burn if the fire comes to them. And we've had a lot of discussions, many of you have followed it, where issues of forest management are brought up. And because we suppressed fires for many years, the forests grew unusually thick, and they're in some places relatively homogeneous. And so they were ready to be chomped on by the beetles. And now we've got, you know, thousands of square miles, literally, over the Western North America, including British Columbia, of dead trees that are subject to combustion. And then we add to that, you know, the winters, the summer storms where you have lightning, and we add to that the propensity for humans to accidentally start fires. And we've got a great challenge ahead of us because we've got a huge amount of standing fuel, and we've got the fuel very dry and ready for combustion. So we're likely to see a continuation of these patterns of long fire seasons and greater and greater fires. This is a map that was put together a few years ago through, in part, the U.S. Forest Service, and it shows the areas that have been impacted by beetles. And again, there's multiple different kinds of beetles, and they're not all dead, but they're the impact, meaning the damage to forested lands, goes from the Mexico border on up across into British Columbia, all the way up into Alaska. So this is a continental scale phenomenon. And the challenge that we have is that when you look for solutions, we talk about forest management, and it's still very much a subject of discussion right now as to, you know, can we really reduce the fuel load? Is there some fashion where we can, you know, literally trim out the forests? And many of you in Colorado will know that that's actually being done up in some of the open space parks west of Denver, up towards in Western Boulder County, Jefferson County. There are programs to thin the trees so as to make them less subject to catastrophic wildfire. But as we saw last summer, you know, the catastrophic wildfires do happen and can grow very, very quickly and cover huge amounts of ground. So that's a topic that it's a little bit hard to see solutions, but there are many, many people working on trying to figure out how to optimize our forest management processes and patterns. And we're hoping that we'll develop some better practices for selective cutting, ways in which we can reduce the flammable character of some of these forests. That's a big challenge, though, not easily done. Let's come back to water. We talked about water. We talked about the sort of the combination of too much water versus too little water. We mentioned sea level. And of course, as sea level rises, there's a huge number of communities that are right at sea level. And we'll just give you the example down in Florida. We'll take Miami as an example, but you could do this in many other places. The city of Miami, as most of you know, is at sea level. And there are now computer programs that are pretty easy to use on the internet. If you poke a little bit, you'll find different organizations, including NOAA, have put together computer programs that have the digital elevation models, which means what is the topography of the coast, and then what does it look like if you raise sea level, you know, 1 foot or 2 feet or 3 feet. And you might say, well, 1 or 2 or 3 feet, that's a lot, but our models indicate that by the year 2300, which, you know, that's a long way away for us, but if you're building a city, that's not that long away. that sea level will rise several feet by the year 2300. And what's that going to do to a community like Miami? Well, we can put onto this map, here's the map of Miami with sea level as it is today. And then the computer can just say, well, what happens if we raise sea level 1 or 2 feet or 3 feet? And Chun is going to show us the effect right there. And you can see that, there's thousands and thousands of homes and buildings that are going to be inundated. And this isn't, you can say it's a hypothesis, but we have the data to tell us that this is extremely likely to happen, and that the people who are living in these areas right at sea level and within 1 or 2 feet of sea level are going to need to take drastic action, whether they move themselves or they build seawalls. Each community is going to take a different approach, and it's going to be extraordinarily expensive for us in the United States, but also for people around the world. I mean, think about people in Europe, think about Holland, think about London at sea level, think about other countries, Nigeria, Lagos at sea level, think about Bangladesh, the whole country essentially at sea level. Think about Shanghai in China. It's at sea level and it's subsiding, and sea level's rising. So this is going to be an immense challenge for the people living in coastal areas. And the other thing that's happening as we get great precipitation events, like what happened when Hurricane Ida came ashore and then brought rainfall all the way up to New England. And some of you might have seen the horrifying pictures of the water coming into the subway stations in New York. It was not a pretty story. And there have been increasing rainfall events all around the world, not only in the United States, but also in Asia and also in Europe. And this is just a picture that we used for the young people the other day, and to illustrate the challenge of a city. I think this is in Austria a few years ago, but there are lots of towns that never thought that their main street would turn into a river, and that does happen. So this is the challenge of too much water, but let's go back to the challenge of too little water. And again, we say that the wet areas are getting wetter, the dry areas are getting drier, and that's because the weather systems are being amplified by the increased moisture in the air. So as you increase the temperature of the atmosphere, it allows more water or more water vapor to enter into it, which is a greenhouse gas, which is a feedback mechanism. But that increased water vapor and moisture in the atmosphere accelerates the storm processes. So storms that were small get a little bit stronger, and areas that were relatively dry have more dry winds. Areas that are relatively wet have more storms. And so the wet areas get wetter, the dry areas get drier. Colorado sits right on the cusp. Eastern Colorado may get a little bit wetter. Western Colorado is definitely getting drier. And the question is, what can we do about this? And how do we handle the increased rainfall in our metro areas? How do we handle our agricultural production in times of diminishing water? And I'm going to again show you a Lego experiment to talk about the characteristics of urban areas to accept moisture. And Mitch and Asa built us this Lego city, and then they rained on it to see how much water would run off from the Lego city. So here's a nice Lego city. We're going to take 500 milliliters of water and put it into a giant storm cloud, and we're going to rain it onto the city, and then we're going to tilt the city a little bit and see how much water runs off. And this was an experiment that you can do it at home. So we were encouraging young people to think about developing observations that they can measure themselves. And here you'll see the water is coming off into this little funnel area, and it's dropping down into a bucket. And we're going to measure how much water comes down into the bucket. So after the rainstorm, the last few little drops of water coming off of the city, and we're going to measure it, and we're going to put it into this graduated cylinder. And look at that, we put in 500 and we get 330 milliliters back. So, some of the water stuck with the Legos, but a lot of it came off. Now here we're going to take the same city and we're going to add vegetation in the form of sponges. So Mitch has added some sponges which represent vegetation, and he's raining on it, same exact amount of water raining on the city. And now it's got some absorbent ground, some sponges, And we're going to see how much water drips off of this village here right now. Here it's coming down into the same measuring cup. We're going to put it into the graduated cylinder, and we're going to see how much water comes off once you put the plants on. And you'll see a big difference. Look at that, 140. So really half as much water ran off because of the absorption of those sponges, which are plants. Well, this isn't altogether hypothetical. We can come to Denver, and for those of you who've been coming to the museum over the last several years, you'll have noticed a massive construction project going on just north of City Park in the golf course. And Kachun's going to zoom us in here. And there's a very interesting thing right across from the zoo in the golf course. They were digging a big hole. I had no idea quite what was going on. And it's going to pop into focus here. But basically, the city of Denver is using this golf course as a way to absorb stormwater. And there's a collection system, and there's a pond, and there's a distribution system for stormwater. And it's designed so that if we get big rainfall events, a lot of the water can be collected on the golf course and then stored in the systems that they're building. And here we've got Kachun on the ground investigating the situation in the golf course just north of the museum. And you can see they've landscaped it. There's a nice little winding stream and a pool for collecting water, which is capable of receiving a lot of water. And many of you will know that the area around the museum, just north of the museum up by 270, floods when there's a rainstorm. And I know because when I drive away from the museum, sometimes there's been a rainy day, I've got to get my little Mini Cooper through a flooded zone, and it's often a little bit precarious. So the city of Denver is taking steps right now to mitigate these heavy rainfall events and to allow the water to seep in. Same thing's going on all around the country. I've seen the same thing being done in New York City. They're actually trying to figure out ways to make Central Park receive more water and act as a sponge in our Lego city. As we back up, we'll now think about other solutions, particularly for agriculture. And I'm just going to comment just briefly because I want to leave a few minutes for questions and answers. But, you know, we use 80% of our water in Colorado and comparable amounts in surrounding states for agriculture. And in Colorado, we grow a lot of food for cows. We're growing alfalfa, grass hay, corn, which we irrigate. And that's going for feeding livestock. And most of the green ground that you see there is irrigated. In fact, all of the green ground, the bright green that you see on this satellite image of the Northern Front Range is irrigation. And the irrigation system varies. There's some center pivots, which are the circles. There's other ways of irrigating rectangular fields. But without that irrigation, the land would be gray or brown as you see it in this image here. And we need to shift our agricultural practices so that we use water more efficiently. And that can be done. And I've been on trips to look at water use in Egypt. I've looked at water use in Israel and water use in Jordan. And in those ultra dry areas, they've experimented with all kinds of ways of growing crops using drip systems. This is in the Negev desert. This is a greenhouse. They're growing melons. They use drip systems that go right to the roots of the melon plants. And if you step into this building, you hit your head on the melons. It's extraordinary. And you're in the howling desert, but they're using water extremely efficiently. And they've recycled the water again and again in order to do this. The concept of recycling water is something that we do. This is a drip system. They're growing olive trees there using drip in southern Jordan. And Kachun, we might look at those couple of water recycling experiments that are being done here in Colorado. And I'm just going to show you, it's close to home. So the city of Aurora, many of you might know about this because the project was constructed just in the last few years. There's a big water return project that takes the water out of the South Platte River and brings it up to the Peter Binney water treatment plant for the city of Aurora. So there's, I don't know if you have a cursor, Katrina, there you go. So the water is cycling around. The people in Aurora are bringing a component, this is just a component of their water supply from the South Platte River, and they're processing it together with groundwater and surface water from other areas, and they're blending it and mixing it. And of course, it's fully treated and wonderful water. And then it goes back into the system, back into the South Platte River, essentially, and it gets recycled. The same thing's happening down at Colorado Springs. If we go down to Colorado Springs, they're looking at ways in which they can bring water back up from the Colorado Springs area up into the Fountain Creek drainage and do the exact same thing, where they're going to take water, again, in sort of a loop, and they're going to bring water from a downstream area through a series of pumping stations and bring it back up and clean it, recycle it. And so there you can see, again, sort of a loop of water. And it's going to be, this one's still under construction, and the water system, I think I drew my arrows backwards. I beg your pardon, but the cycle is coming down the stream and then up through those pumping stations, and it's going to provide recycled water in the Colorado Springs area. And of course, both the city of Aurora and Colorado Springs are benefiting from water from the Colorado River system. So the fact that we can use it more and use it more efficiently is a great advantage to us, particularly as we struggle to collaborate with our colleagues downstream in the Colorado River system. So what I wanted to do here is just illustrate that we do have technical solutions for some of these challenges that we're facing. And I encourage young people to think about careers that are in the direction of renewable energy, efficient water usage, batteries, ways in which water can be used more effectively. And there are many, many technologies that are being innovatively looked at all around the whole world, and we can find those best practices and use them here in Colorado. And I, you know, for the young people, my last comments here, I'm just going to give you a couple of more comments. I wanted to make them recognize that they're not alone in this exercise. When you talk to a high school student, you know, think about somebody who's just realizing the situation of the world. You might have seen that cartoon in the Denver Post a couple of days ago with the young student carrying the world on their shoulders and saying that, you know, they thought their backpack was heavy, but the world is a really heavy thing. And I wanted to offer solace to young people, and I did it through the words of their peers. And for example, Amanda Gorman, the young poet who spoke so eloquently at the inauguration back in January, she said, you know, the last three lines of her poem were, and I'm quoting her, so she said, "For there is always light, if only we're brave enough to see it, if only we're brave enough to be it." And so Amanda is, of course, telling people that there's always hope, there's always light, but we need to have the courage to go forward. Malala, who many of you know, Malala Yousafzai, who was she's the young woman who was shot by the Taliban back in northern Pakistan quite a few years ago. But she said, "One child, one teacher, one pen or pencil, and one book can change the world." And of course, she's thinking about the education of young people, of women in particular, in Pakistan. And that's something that's happening right now. And of course, we're hearing on the radio today about the challenges of educating women in Afghanistan. That's going to be a challenge of our time, but we're working on it. And then Greta Thunberg, who many of you know, and she gave a talk here in Denver a couple of years ago, but she says right here, right now is where we draw the line. The world is waking up and change is coming, whether we like it or not. And so Greta, together with Malala and together with Amanda, have helped raise the consciousness of younger people and all of us. So I think we live in times of great change, but we live in times of great opportunity as well. And we need to have the young people have the courage and the spirit to carry things forward. So it's almost 8 o'clock now. And of course, if anybody needs to leave, of course, you please do. But I'd like to take maybe 4 or 5 minutes. It might be Mitch, if you can spot some things in the chat. If there's some questions there, maybe Chun and I can address them. Let's see what people are thinking.
Absolutely, and thank you everyone for joining us tonight. And as Bob said, if you need to go, we totally understand, but we're happy if you can stick around. The first thing is we have a survey tonight to evaluate this program, and I'm putting that link in the chat. And if you have a moment to fill that out, that would really help us. So thank you. So we have a question here about photosynthesis. Photosynthesis, plants take in carbon dioxide and sunlight and water and output sugars and oxygen. Are there any efforts to replicate that in our cities or something like that?
Well, I've heard the phrase, there's a phrase of people that want to hack photosynthesis. That's what it is, hacking photosynthesis. So you might hear, I'll bet if you Googled hack photosynthesis, like computer hacking, you'll find there is a huge effort going on right now to understand how to increase the efficiency of photosynthesis and things like growing algae, things like treating seawater so that you can have phytoplankton flourish more efficiently. Those are being experimented with right now. And of course, many of you will know that the reason that we can support the people on the planet Earth today is because of the efficiency of our agriculture. And that's highlighted by the Green Revolution, so-called. And certainly I've seen it in my life where the increased yields of rice and wheat have been astonishing. And those have been associated with different strains of wheat and rice, also the use of chemical fertilizers. But it's something that there have been huge advances just in my lifetime. And I think as we go forward, I can anticipate many additional changes, and that'd be a career path for young people. So for young people who are interested in biology and botany, think about increasing the efficiency of photosynthesis. A great idea.
Yeah, great idea. Let's all get to work on that. Another question is about the all our satellites that monitor and collect all this data have been around for a while, and are they aging and failing, or are they being replaced?
Well, I'll comment on that, and then maybe Chun might want to bring some more information. But I'll say that I noticed in the newspaper the other day that we're approaching the 50th anniversary of the Landsat program, and I grew up with Landsat imagery. It first became available in 1972, and that I think we're on Landsat 9 right now, if I'm not mistaken. So the Landsat system, which is a satellite orbiting the Earth, looking specifically at Earth and Earth resources, primarily designed initially for vegetation studies, that satellite system has been continually upgraded. So as one satellite fails, another one comes to take its place. Now that involves continuing investment by NASA. And Chun, you might have I don't know if you want to chime in here on the future of satellite technology. And
yeah, I mean, we saw that in the sea level rise curve that we showed earlier. And Bob didn't mention this, but you might remember there were a bunch of different colors, and each color was actually associated with a different satellite. And so as satellites age out, and the scientists who build the satellites, who plan the satellites, they know that the satellites that they're building have a limited life. And so they are always working to create the next generation of satellites. And so in many ways, we are living in a golden age of Earth exploration. So not only exploring outside of the Earth into outer space, other planets, other solar systems outside of our own solar system, but we have this golden age of where we have increasing amounts of data that are being returned from Earth observing satellites. And it's really these satellites and the data that they provide that help us plan and to help us understand and to model how our climate and how our environment is changing. So satellite systems are actually extremely critical to our understanding of planet Earth.
And I'm noticing a comment in the chat. I think it's Doug's telling us that the next Landsat is going to get launched on Monday. So this is an ongoing story, and I think it's super important to appreciate that we live in unparalleled times of data abundance. So the challenge of dealing with all the data, understanding the significance of the data, recognizing the subtleties of the data, those are the challenges that young people are facing today. And they will use the tools that we have built, which include things like Wikipedia and other tools, to make the world a better place. And Mitch, maybe one or two more questions?
Yeah, so we have a question about Hurricane Ida and heavy rainfall events. People have seen in the news that they're getting amplified and speeding up in ways they didn't used to. Can you talk a little bit about that?
Well, I think people are always a little bit hesitant to point their finger at an individual hurricane, an individual storm. And you've sort of heard the story that any individual event might just be that capricious, character of nature. But if you start looking at it on an annual basis, and people will do this is going to be the big data story. I might ask, well, how many, ergs of energy were involved in the storms? And someone's going to calculate this. Some bright young graduate student will figure out, how many, ergs or some measure of energy were involved in those storms. And then you'll try to figure it out over the course of time. And our computer models would indicate that those are going to become more energetic. So again, I might say if I was sitting in Central Park and I got a record rainfall, I can't remember the specific numbers, but you might have noticed this, that they got record rainfall in City Park. It was like a 500-year rainfall event. And then the next week they had another 500, or 10 days later, they had another, it rained like 3 inches in an hour in Central Park during Ida. So we are seeing, evidence for increasing, storm intensity. And I might say that we're at the beginning of the curve now, but it's the kind of thing that more and more people are watching more carefully. And I think that you will see a correlation between increasing temperatures and increasing storm intensity.
All right. And so I'm not sure if you've heard about this, but apparently Iceland has a geothermal generated carbon dioxide recapture system. And do you know about that? And are we doing anything like that in the US?
So it's absolutely a wonderful thing. It's inspirational, and it's called Helga Shelley or something. It's right near Reykjavik. It's a big geothermal plant, and they're taking essentially, I'm going to say free energy, because it's geothermal energy in Iceland, and essentially free energy. And they've got lots of water in Iceland, and they've got a system that'll take carbon dioxide out of the air and put it into water, so carbonating the water. And then they're injecting it into the ground, and Iceland has a lot of basalt. In fact, it's made of basalt. And so you've got three things. You've got infinite energy, very cheap. You've got lots of water, and you've got lots of basalt, which is volcanic rock. And the carbonated water goes into the basalt, and it makes calcite. Calcite is CaCO3. It's a mineral, and so it's permanently locked into the basalt. Now, you can quickly think about the world and say, well, where else do I have, free energy and lots of water and lots of basalt? And, first thing I thought of was maybe parts of Kenya, central Kenya in the Rift Valley. There's a geothermal system there, so they've got lots of energy. There's a fair amount of water. You could argue about how much, but they've got a lot of basalt in the Rift Valley in central Kenya. But another place that might come to your mind is not too far from what's behind my view here. This is coastal Oregon, but if you go to the Pacific Northwest, the Columbia River basalts, they're called, is sort of the eastern side of the Cascades. There's very inexpensive energy. That's where we smelt aluminum, because we're using the water from the Wachumedinga Reservoir to make hydroelectricity. So we've got inexpensive energy. There's fair amount of water in the Pacific Northwest, although they've had dry conditions. But you've got the Snake River, the Columbia River, Fraser River. There's water up there, and then of course you've got lots of basalt with the Columbia River basalt. So that which you're seeing done in Iceland, which is it's a prototypical project. It's 4,000 metric tons of CO2 per year right now, which is a small amount. But if it's a proof of concept, there are other places where we can do it, and the future is exciting.
All right, wonderful. I just want to make sure that I put up our credits. So we give credit, oops, and I put up the wrong thing. Want to give credit to all of the people who produced all the amazing data visualizations we were able to use. And one last question, somebody missed that last part when you were quoting Greta Thunberg. So could you remind us what that quote was?
Well, so let me just say that Greta, I hope you all know Greta. So Greta is this remarkably poised young lady, and she gave a talk like 2 years ago, and I think I give a fair number of talks, and I think I can sort of talk, but she gave the best talk I've ever heard in my life. And she was like, 14 or something at the time. And one click on Google, you'll find it was called "We Live in a Strange World." So if you really want to hear Greta at her best, go find her giving her "We Live in a Strange World" talk. It's absolutely one of the best speeches that's ever been given. But the quote that I had was one of the, it's more along the lines of what she said here in City Center Park in Denver 3 years ago. She said that right here, right now is where we draw the line, meaning her generation is drawing the line. And she says the world is waking up and changes are coming whether you like it or not. So, you know, Greta is very forceful. She's in a hurry, but she's right.
All right, wonderful. Well, I think that's the time we have tonight. Thank you everyone for joining us. Thank you, Bob, for that wonderful presentation. Thank you, Chun, for that wonderful presentation. And I hope you all join us. Our next Digital Earth is November 17th, and we'll be looking at changing Colorado. So we hope you can all join us then. And thank you so much. Everyone have a wonderful Wednesday evening.
Good night.
Yep. Bye.